what are some of the technical things that we can do in order to have a better chance at execution and dealing with uncertainty? And so the thing about dealing with an uncertain problem is you have no idea how big it's going to be. You don't know how long it's going to take. You have absolutely no idea how to deal with this thing. So how do you deal with it? How do you solve these big infinite problems? And the key is to make them small problems. This is actually one of the first things you learn at MIT, and that's that there's no such thing as a big problem. A big problem is something that gets partitioned into small manageable problems. You solve the small manageable problems, and then your challenge is integrating everything back together. And so the first part of making it smaller is look at the history of what's actually been done, because there are lessons to be learned there. Not only that, but right away you learn, like, for example, you can't make this for under $10. Guess what? That now becomes a boundary. Your problem has become smaller. It's no longer infinite with regarding cost. And so you have to look at your project goals. And so you have to put certain things in the sand that are non-negotiable. And so that'll help you define how big your space are and limit it. And so the next part is when you do experiments, and this is where you have a lot of bad experimenters, and PhDs are among them. PhDs tend to be, they like to play, and they don't design experiments well. And the key designing a good experiment is no matter what the outcome is, it yields data. You learn something. This is how Dr. Cho completed his entire doctoral research in 1.5 years, whereas it takes other people 3 years or longer. And it's because every experiment I designed, if it didn't work, I learned something. And so it made my problems smaller and smaller and smaller. So instead of dealing with this big massive glob, I'm only dealing with this. In terms of doing experiments, you have to get into the mindset that it takes time. And so how do I manage that time? And what time is, it's the period of how long does a step take times the number of cycles that I need. So how do I reduce this? I either need to shorten the cycles, reduce the number of cycles, or do both. That's how I speed things up. But first you have to establish, when you look at problems like this, how do you gauge it? The other part of it is when you look at tasks, what are the tasks that are in parallel and what are in series? The advantage of steps that are in parallel is you can work on them all at the same time. So this is where getting more people working on problems and things like that really speeds things up, because you're all working in parallel. However, you have to figure out what steps are in series. Those are the things that you can't get around. Not only that, the tough thing about series processes is step 1 doesn't work, then guess what? It doesn't matter what you do on 2, 3, 4, and 5, because the whole thing won't work. It's a chain. You only need one link to fail for the chain not to work. And so, actually we used to joke, the limit is 9 women can't have a baby in 1 month. It just doesn't work that way. Now, after you've made sure that every step works and that you figured out the series process, when something breaks down, you have to maintain your series discipline, and it's called the onion. And that's that you have to account for the outside layers first before you can make any conclusions about the inside layer. An example of that is actually IT. When you call up the IT department and say, hey, I'm having a problem with this, you get offended because the first thing they say to you is it plugged in? Have you turned it on? You think, what do they think? I'm an idiot? But when you sit down and think about it, in the absence of any other data, that's the outer layer of the onion. It doesn't matter what the BIOS system is doing or anything else if the thing isn't plugged in and if the thing isn't on. And so this is an example of unpeeling the onion. Integrating both ideas of these steps and trying to reduce the number of them This is actually Dr. Cho's secret sauce to doing process development. Process development is extremely difficult because you're dealing with the forces of nature and you're trying to harness it. And in chemical processes, they're in series. You just need one of those steps to fail and the whole thing won't work. And then you have to figure out, well, what did work and what didn't work. And so what Dr. Cho used to use is a technique called the step technique. And I would start out with 100 wafers, and then I would work on every process in parallel. So the first thing I would do is go to step 2. If step 2 yielded, then out of those 100, I would bring 75 wafers up, all to that point. And then step 3 works, and I would bring 50 wafers up. So I would keep dropping 25 wafers at a time. Well, what happens when you get to step 8 and it fails? Well, the guy who works serially, he's got to go all the way back to step 1 because that's where his assets are, because he's working in serial. Dr. Cho, by using the step technique, guess what? If it fails at step 8, I only have to go back to step 7 because I got wafers sitting there waiting to be used and already. And then I can do these short loops, and I can do it very quickly instead of having to go all the way back. Your team and how they execute. Not everybody can handle uncertainty. The cultures I used to create is a culture of throat cutters. Not cutthroats. Cutthroats are people who stab you in the back. Throat cutters are people who can take a project and complete it, and it's done. It doesn't pop up again. It's not a problem again. They understand that working with uncertainty is the dragon. It's the beast. And when you get the beast down, cut its throat. Make sure it doesn't pop up again. And this happens very often in engineering where they have bad solutions. Things are done incompletely and it just comes and bites you in the ass again. You need heavy lifters. Edison was right when he talked about the 99% perspiration. Yes, you think of things, but then it's all about executing. And the thing I used to like about that part is, guess what? This is now about will. And my will is going to be stronger than somebody else's, and this is where I can win. But you need heavy lifters. You need those people who can do a lot of work, who can churn through a lot of work, have enough energy to do it. And people don't recruit for that. I almost got fired because I passed on a Stanford PhD to hire a gal out of Northern Illinois University, which is a glorified high school, because she was a heavy lifter. And I told them that the last thing I need is another PhD to tell us what we're doing wrong. I said, we need people who can be productive. You need a mix of people. Somebody's got to do the blocking and tackling. And you don't need know-it-alls. What you do need are people who are resourceful. You don't need people who think they know the answer. Because if somebody knew the answer, then it would have already been done. You need people who can go out and find the answers. You also need realists, people who can come to grips with what you're actually dealing with and not what they perceive what you're dealing with. You can say, and this actually happened to me in an interview. I was asked, are you a half full or a glass half empty kind of guy? And I said, neither. I'm a guy who says there's 4 ounces of water in the cup. I said, I don't take a bias, a positive or negative or whatever. I just deal with the reality of the situation as it exists. And that's the kind of people that you need. The next section is now we're ready to execute. And so these are the emotional issues that I have to deal with.